Okay, so now we're going to talk about the periodic table and how these elements are put together. And Mendeleev is credited with being the first person to put a periodic table together. Now, there were other scientists that were working on it, but even today in academia, it's who publishes first. So he published first. So he was a Russian scientist born in Siberia in 1834, and he is known as the father of the periodic table. He basically set out to identify a pattern in the elements, and that's based on his experiments that he did with them and physical and chemical characteristics and properties he knew about them. And Mendeleev wrote facts about the elements on individual papers and individual cards, and he noticed that there was a pattern when the elements were arranged in an order of increasing atomic mass. So I want you again to remember what atomic mass is, okay, and realize that he actually was almost correct but not completely correct in that assessment. So his table wasn't perfect. Arranging the elements by increasing atomic mass left 3 blank spaces. However, he said those elements would be discovered, and they would have very similar characteristics as the families that they were in. And so he was able to predict properties based on the family that they were in, the column that they were in. And he published this table in 1869. So that's kind of like what his first table looked like. He was actually just trying to write a textbook for his students. This is what kind of started this whole thing, is he wanted something that he could give to his students that they could study from. So, and within 16 years of the first periodic table, chemists had discovered all of the missing elements that he had left rooms for, or spaces for: scandium, gallium, and germanium. Now, he did not have the noble gases on there yet, and he actually did fight to not have, he didn't believe that there were noble gases, so he was not perfect. So working with Rutherford, Moseley, a little bit later, found the elements fit a pattern better when arranged by atomic number, not atomic mass. And if you notice in your periodic table, and take a second to do that, you will find that there are, if you look at atomic masses, generally they do increase, but there are some exceptions within the table. So take a look at those atomic masses. Those are the numbers with the decimals after them, right? And look through it, and you'll see that there are a few places in the table where you have an atomic mass followed by something that's not greater, it's a little less. But if you put them in atomic number, it is perfect. 1, 2, 3, 4, and so on. And so this is where the periodic law came from, that if you can arrange these in basically it's groups of 8, the physical and chemical properties of the elements are a periodic function of their atomic numbers. They did eventually add the noble gases. They discovered them, and they were really hard to find because they are unreactive. That's why they're called the noble gases. They don't associate with all the lower elements. And that was the last group. Okay, so you definitely want to write this on your periodic table with Sharpies or pens or whatever, and that is that the group 1A are called the alkaline metals. They always form a +1 when they react. I think people think that they always have to have a +1 if they react. If they don't react, then they don't have any charge. Group 2s are called alkaline earth metals. They always form a +2 when they react. Now, we're going to skip that middle section. Those are called the transition elements, that middle chunk right there. Skip over that, and we're going to go to the next group, which is group 3A, 4A, 5A. When we get to 6A, that's the oxygen group, and that's, of course, the first element there is oxygen. And that family, that column, they tend to form -2s when they react. Group 7A are called the halogens, and that starts with fluorine. Fluorine is the group leader there. And fluorine, chlorine, bromine, iodine, and astatine. And they always form a -1 when they react. And then lastly, we have group 8A, the noble gases, and they just don't react. Now, there have been scientists that have forced them to react with things, but generally speaking, they're not going to react. In the middle, the metals we kind of skipped over and didn't give them a group number. Those are the transition metals. There's also on your periodic table a stair-step line. Highlight that, go over that with like Sharpie or pen or something. that separates the metals and the nonmetals, because it's very important for us to know which elements are metals, which are nonmetals. Okay, what we know about metallic properties, or metals, is that they're good conductors of heat and electricity. So that's why we use copper wiring. The heat, like if you use, well, let's just get into a car on a very hot summer day. The seat belt buckle is super hot, in fact, almost hard to touch. And the other parts of it aren't so bad. They're hot, but they're not that hot. Malleable, you can, bend basically. A ductile is you can pull into wires. High luster, they tend to be very shiny, and they're usually solid at room temperature, but there are some exceptions. Mercury and cesium are very close to liquids. Mercury is a liquid, but cesium is very close to a liquid. I misspoke there. There's also gallium is really close to a liquid, and in class I'll tell you the story of the disappearing spoons and scientists' practical jokes on each other. On the table in the front, usually all the elements that are in black are solid at room temperature. Blue, they're liquid at room temperature, and mercury and bromine will be the two that you see there. And then gases are in red. Okay, non-metallic properties for the nonmetals, they tend to be brittle, they shatter, they don't bend, they don't tend to be very shiny, again, there's some exceptions, and they don't tend to be good conductors, they're insulators. Metalloids, those are elements along the stair-step line, have characteristics of both metals and nonmetals, so these are your metalloids or semi-metals. Sometimes you'll hear that term semi-metals too. And so then you will get characteristics of both kinds. So there's usually about 3 different groupings you can make in a periodic table. Those that are true metals, those that are true nonmetals, and those that are a little bit on the edge there, a little bit of both. Okay, natural state of elements. Usually you do not find elements on their own. Sometimes, you'll have a copper mining or gold mining, and you will find these noble metals, silver, platinum, gold, copper sometimes, and gases are found in nature uncombined. Okay, most everything else is going to be in an ore or an alloy of some type. Diatomic elements, again, I brought them up last chapter. Definitely make sure you know what those are. You can remember by halogens, that might be something, because all of the halogens, FCl-IBr, okay, I don't include astatine because it's so rare, but all the halogens are diatomic when they're alone. And then H, O, and N, Hun, those are also diatomic when they're alone. Now when they react, we kind of put down on our table what those are. All the halogens tend to form a -1, oxygen's a -2, nitrogen's a -3, and hydrogen's +1. But when they're alone, they're diatomic. Okay, and here's kind of, sometimes this is red actually, red or green is a gas, blue is a liquid. Depends on the table that you have. And these are close to being liquids. Okay, you just have to hold them in your hand and they'll melt. Okay, some ions. We looked at this before. Metals, but I should categorize. Metals lose electrons to form positive charges. Those are called cations. If you can think of like cats, if you like cats, those are positive things. Nonmetals gain electrons to form negative charges, and those are called anions. So take a little bit to make sure you got that, because those are very fundamental to chemistry. The two things are now attracted, and they come together with a 0 net charge. That's where you're going to get your stability. Okay, so just to recap, a cation is a positive ion, and that's a loss of electrons. So for instance, you'd have a calcium +2. That'd be a cation. Sodium +1. An anion, a negative ion, would be a gain of electrons. Oxygen -1, -2, fluorine -1. And then the compounds have to come together to make a 0 net charge. So if I have an aluminum +3, and I have a Cl -1, and this is a really good visual to get in mind here. What I'm going to do is I'm going to take 3 chlorines, which I put a subscript here, and 1 aluminum. Now, as we're just starting to put these together, if you want to put their charges up on top as superscripts, absolutely do that. But the compound includes 1 aluminum and 3 chlorines to make a 0 net charge. for aluminum plus 3 and O minus 2. I guess I shouldn't have done that. Let's just go ahead and redraw that. What is that going to look like? Well, we're going to have how many aluminums and how many oxygens? Just let's think about that. We are going to have an Al plus 3 and O minus 2. Well, let's do another one. Oh, that's a minus 4 and a plus 3. Well, that's not going to work. Now we're going to have a plus 6 and a minus 4. Well, that won't work. That'll work. That'll give me a plus 6, a minus 6, and now I'm going to have 2 aluminums and 3 oxygens. 2 aluminums, 3 oxygens, and that's the compound. And again, if you want to keep their little charges up there, absolutely do it, but make sure you got that 2 and that 3 as subscripts indicating how many there are. And then if I had aluminum and phosphorus as a plus 3 and a minus 3, just need 1 of each, and we've got a 0 net charge. A couple things about ionics. They will dissolve in water to free their ions. Their ions will close a circuit and conduct a current. You should YouTube having an open circuit with a light bulb and putting it into an ionic solution. Their ions could also be freed by melting it. It's just that they tend to melt at a very high temperature, so it's pretty hard to melt them. Now, non-ionic compounds, which we're not going to study for a little bit yet, they tend to melt at low temperatures. They do not conduct a current. But we're going to focus on ionic, the positives and the negatives, for a while yet.